All right, lecture number 15, Intro to Reinforcement Learning. This is one of my favorite topics in the course. I've got a soft spot in my heart for search because that's what most of my research is on, but I've also done research in reinforcement learning. And I think you're going to find it to be pretty fun. The textbook for the course, or the optional textbook, even though it's optional, I do highly recommend reading the relevant chapters and following along with it because it is... This book by Sutton and Bartow is kind of the Bible on reinforcement learning, or at least the pre-deep reinforcement learning, where you start to get into neural nets and stuff. I'm not sure if it has that part in it. Maybe it's been updated since then. But it's certainly been around longer than deep reinforcement learning. It's very understandable, reads kind of like a novel with some equations in it, so I highly recommend it. I actually read it for the first time on a plane, while I was studying for my reinforcement learning exam. And it's also, I have a hard copy of the book, but you can read it in HTML on this website, or on the website you can also download a PDF version of the book. So I don't like paying a lot of money for textbooks, and I'm sure you don't either, so this book is out there for free. And the two authors of the textbook, if you've been following along on Discord, Andrew Bartow and Richard Sutton, just won the Turing Award for reinforcement learning. So if you're not familiar with the Turing Award, you should be ashamed of yourself as a computer science student, but this is essentially the Nobel Prize of computer science. And they got it for their lifelong work in reinforcement learning. And I was very lucky that when I went to the U of A for my PhD, I took the reinforcement learning course, and Rich Sutton actually taught that course there. He taught it along with another professor, but it was great, and he's a wonderful person, and I'm glad that he received this award. So it's cool that I get to put that slide in there now, because it's very rare that you have a professor who actually goes on to win that high-level award. You will never be able to give that slide about me because my research is not this world-level quality, but I like video games, so I might not win a Turing Award, but at least I'll have fun, right? So what is reinforcement learning? Who here has dabbled in reinforcement learning? Anyone? A couple of people? That's cool. First of all, I understand that there is a math course on reinforcement learning, and someone told me last year that we cover almost the same topics that they cover in their whole course, which must mean that they go into great mathematical detail about everything. You're nodding your head. Did you do that course? Okay, so we will not. We are more concerned with it algorithmically, and I want to teach you enough about it so that you understand it conceptually, you know a little bit of the math behind it. We are not going to do any of the proofs that show that all this converges and stuff like that, but at the end, you will definitely know enough to implement tabular reinforcement learning. So there's two main types, I guess, of reinforcement learning, and we'll talk about this as we go along. Tabular reinforcement learning just means that you can fit the entire state space into a reasonably sized array. So that's the table. The table holds the policy. So we're only going to be talking about problems and environments where the whole state space can fit in an array. And then if you talk about deep reinforcement learning, that is where your state space is so large that you can no longer fit it into a table. So what they do in deep reinforcement learning is, instead of having a tabular policy, they have a policy that is contained in a neural network, right? And so the deep neural network part, that's where deep learning comes from. But a lot of the mathematics is still the same. It's just now, then you'd be updating a neural network instead of a table. So in a hand-wavy way, it's all the same reinforcement learning methods, and it's the same problem statement. It's just a different way of representing this table of values that you need to do the math. So reinforcement learning is a sub-area of machine learning. As you're probably well aware, probably 90% of the world thinks that AI is only machine learning. But now that we've done the first half of this course, I hope you're aware that it isn't. And there's been a lot of AI over the years that has nothing to do with learning at all, let alone these topics of machine learning. RL is inspired by natural systems and psychology. So one of the reasons for reinforcement learning is that it kind of mimics the way that living organisms learn, right? So I try something good happens, then in the future I might try that again. If I try another thing and I get burned or bitten or whatever, maybe I won't try that thing again in the future. This is exactly what we're going to be doing, just with math. So the way this works is it's going to learn via interaction with the environment. And so you're going to be an agent in an environment somehow, and you're going to try some things. You'll see what works, you'll see what doesn't work, and you'll update your beliefs based on that. This may seem a lot like search at a very high level. In one way, it kind of is, but in another way, it really isn't. So we'll see later on that there are actually methods that combine search and reinforcement learning. But reinforcement learning does need to explore the state and action space, but just not in a necessarily exhaustive way like something like A-star or BFS would do. As agents take actions in the environment, they receive rewards, and those are numerical rewards, so some real valued number. So a good action, meaning here, a good action would be something that leads you toward the goal that you're trying to achieve. That will give you a positive reward, and a bad action, meaning that it's not necessarily helping you achieve your goal, would receive a negative reward. And the reinforcement learning agent's goal is to maximize its rewards. More explicitly, as we'll find later, it's trying to maximize the expected sum of future rewards. But in essence, we're just trying to get as many good rewards as possible. So I'm sure you're all familiar with what machine learning is at this point, but just as a brief overview, the three main types of machine learning that are popular these days are unsupervised learning, and I'll talk about these in a bit, supervised learning, and reinforcement learning. So you may have seen these in other courses, maybe not reinforcement learning, but let's talk about the differences between them before we dive into more RL stuff. So within machine learning, the more popular form that you see traditionally is called supervised learning. That is where you learn from training data. So you have a ton of data. You are given the inputs to that data. Maybe it's an image, maybe it's some X and Y values, and you're given what the real answer should be. And then you learn to predict outputs for new unseen inputs given all that stuff, right? So you're given a bunch of pictures of apples, oranges, pears, whatever. You're given what they really are. You may have some initial guess with whatever algorithm or model or neural network that you're using. And over time, as you refine your results, you get better and better at being able to classify those types of things. Unsupervised learning is, it's really hard to come up with like a really strict definition of unsupervised learning. But really what it is at heart is you give a unsupervised learning method a bunch of data, and what it does is it tries to learn from that data without all of these explicit training samples or proper input-output pairs and stuff. So one common thing that happens in unsupervised learning is like clustering, right? You give it a bunch of data, you say, does this fit nicely into different groups or something like that? And I'll have an example of that in a second. So a really popular example of supervised learning, like I just talked about, you have some input raw data. So for example, you're going to have, let's say we're trying to classify images of fruit or vegetables, or anything. It doesn't have to be fruit, obviously. But over here we have some tomatoes, maybe we have apples, pears, oranges, cherries, etc. And so there's going to be some sort of supervisor, and the supervisor lives within the algorithm. And the supervisor is going to say, okay, Mr. Algorithm, what do you predict this image is? Oh, you said this was a pear, but it's not a pear, it was supposed to be a tomato. So whatever happens in that model to update its values so that the next time you're passed in a similar image, it predicts something closer to tomato, that is the training process, okay? So you get a bunch of data, a bunch of labeled samples, it processes them, so maybe you have 100,000 images and 100,000 samples and you pass it through your algorithm. So this is the training step. And then at the end of each training step, but mostly once you're done all the training, what you're left with is a model. So it's an algorithm which has some parameters that have been tweaked, whether or not it was a neural network or a support vector machine or a random forest or whatever it is, you've tweaked some settings inside that model to be able to ideally more correctly classify these things. And so by the end, now you'll be able to pass it in a new image that it has never seen before, and it'll correctly say, oh, this is a tomato, or this is whatever, right? Supervised learning examples fall into one of two main categories, one of which we just saw was called classification. So in classification, over here, for example, the output of your model, given an input, is one of a finite set of things. It was a tomato, a pear, an apple, whatever, right? So your output of the model might be some integer, right? Or it might be a vector of ones or zeros representing what fruit it was. So that's a classification problem, but it doesn't have to be as complex as that. Classification could just be x, y points on a plane. And so some very simple classification problems, for example, just draw a line through that plane to try and separate categories into two things. Turns out this is kind of what a neural network does, just a lot of times. And we'll get into that once we get to the neural net lecture. Another type of problem is called regression, where it's more of a function approximation, right? So instead of classifying something into a finite set of classes, instead, this is like, okay, given this x value, what is the y value? And that could be a real valued number. So let's do a regression example here. Put your hand up if you can spot the pattern. We are all very good at these. I'm sure you've seen them on Facebook, where it's like only 1 in a trillion people are smart enough to answer this very simple but ambiguously worded problem that is specifically designed to get people hating each other in the comments. So if x is, okay, here are my 3 sample points that I'm giving you. X is 1, y is 1. X is 2, y is 4. X is 3, y is 9. If x is 4, 16, right? So I could have said, haha, it's not that one. I could have come up with some other function, but yes. So you get a bunch of input x's and output y's, and you try and learn some sort of function that tells you what an unseen x values could be. So in that case, I was just squaring the value of x, right? So there's lots of different algorithms that will do that for you. Here's what this looks like over time for regression. You get this line. Sometimes there's linear regression, polynomial regression, all types of nonlinear regression algorithms. And over time, as you learn and learn, you get closer to the true value. Now, of course, real data sets are kind of noisy, so that even though this data set does sort of follow this pattern, it's not necessarily the case that in actual science, when you're going out and taking measurements, that you're going to get the exact x squared, really nice regression formula. But it is nice to come up with a formula so that if you are ever trying to make a prediction, like in the real world about, okay, now we have this sample we've never seen before, what should the output be? At least you can make an educated guess at what that should be. Unsupervised learning. This is an example, if I can't zoom in because it's in PowerPoint, but here we've got a bunch of different hand-drawn digits. So the digits 1 through 9. And so I've given, oh, well, I didn't do it. Someone gave this unsupervised learning algorithm a bunch of hand-drawn characters, and it has classified them into different parts of this geometry, right? So let me go forward. I have a bit of a better example of this. Here we go. So whatever this unsupervised learning algorithm has done, it has detected some qualities of these input images which are similar, and then grouped them to be able to be visualized in some sort of space, right? So we can see here, for example, all the zeros are sort of up here in this cluster, a bunch of 8s here in this cluster, 6s down here, 7s down here, 9s here. But you can also see some misclassifications where we've got things like 8s in around the 3s, maybe some 1s in around the 7s, because different people write in different ways, right? And so the characters which have similar characteristics have been grouped in some sort of way. Now, this is not an unsupervised learning course, so I'm not going to go into the details of that, but it is very interesting. And unsupervised learning, in my opinion, is one way that if you're like at a business, for example, and you've got a bunch of data, customer data, whenever anyone asks me for advice on AI, my very first thing that I always say is try and visualize the data in any way possible. Because if you are able to cluster patterns and stuff, maybe you could say, oh, the customers who like this also like this or something, right? And maybe you can make some more money. So visualizing the output of unsupervised learning is a great way to see patterns in data and then hopefully be able to make some take some actions based on that stuff. So what is reinforcement learning then? Reinforcement learning is not an algorithm. Okay, some people might say this is a reinforcement learning algorithm. What they mean, or a reinforcement learning method, is that this is an algorithm, of which there are many, in which you can solve a reinforcement learning problem. Okay, so RL is really more of a problem specification. So just like in order to do search, we had to form our environment and our actions in a specific way, or to put something into a genetic algorithm, we had to have a specific representation with a fitness function. Another similar thing is going to happen with reinforcement learning, where we've got to be able to specify the problem in a specific way. And once we have that specification, then we can use some sort of algorithm to solve that problem. So many reinforcement learning or algorithmic techniques can be used to solve reinforcement learning problems. And as I just said, any RL method, that's probably what people are going to say, is a method that you can use to algorithmically solve one of these reinforcement learning problems. Now, when we say solve, reinforcement learning is a sort of learning process, right? So by solve, we don't necessarily mean get the best possible answer all the time, but we mean get closer and closer to the real true values, right? Because we may not be able to get there exactly, but we can get closer and closer and ideally learn some things that can help us. So reinforcement learning, as I said, is learning via interaction with the environment. Unlike supervised learning, there is no explicit teacher for learning. So no one is saying, this is an apple. What would happen is you could say, okay, if you correctly classify it as an apple, I'll give you a little treat, right? Or if the baby touches the hot stove, they'll be burned, right? So you're going to try things and then see what happens, take that reward, and then update your belief of what is good to do at this particular state. So the agent is going to take some action, it's going to and then receive a reward signal from the environment. And what's very, very important here is that the environment, the problem description, is in control of the rewards, right? The agent just doesn't get to say, here is my reward from doing that thing. Because if the agent was in control of the reward, it could just give itself all the treats in the world, and then everything it did would be wonderful because it could always just give itself rewards. So the environment is in control of the reward, and you can think of the reward kind of like a fitness function or an evaluation function, right? At some point, if we are doing reinforcement learning, we have to come up with a reward signal, this function, I did this thing at this state, here is the number that you now believe that value of that reward, and we have to come up with that thing, right? If we're doing pathfinding, the reward may be related to the distance traveled. If we're doing, if we're playing blackjack or some other card game, maybe it's the amount of money that we won is the reward signal. So yes, we still have to come up with the reward signal, but the agent is not in control of giving itself rewards. So learning via interaction teaches about cause and effect, the consequences of actions, and what to do in order to achieve that goal. And just like the goal of solving a problem in a genetic algorithm or an evolutionary algorithm was related to the fitness, the goal is going to be somehow related to the reward in reinforcement learning. So here's a nice little diagram. Over here we have our environments. The environment defines the states. It defines the actions that are available to be done at those states, and it also defines the rewards. And so the way the rewards are defined is typically you have some function, which is a reward function, you pass it in a state and an action that you did, and you'll get a reward. In reinforcement learning, what we'll find is that these rewards and the actions do not have to be deterministic. So reinforcement learning can deal with randomness, whereas something like search can't. Well, search can, but you have to modify those algorithms. Like A star, BFS, DFS, alpha, beta do not work out of the box in games or environments with randomness in them. You have to modify them in order to get them to work. But with reinforcement learning, let's say we're playing a card game like poker or blackjack. If I take the same action at the same state, sometimes I might win and sometimes I might lose, right? And the idea here is if I try that enough times, we will figure out the expected value of those actions over time, right? So if I'm playing poker and I go all in with pocket aces, sure, there might be a time that I lose, but I will probably win the majority of the time. So over time, you keep going in all in with pocket aces, or you keep betting with pocket aces, you win maybe 75% or 80% of those hands, and then your value of saying, okay, I have pocket aces again, what should I do? It'll say, well, you're probably going to have a good return on that investment if you bet something with pocket aces, right? So the environment has the states, the agent does the action, one of the legal actions from that state, and then the environment says, okay, based on the action that you did, here's the next state, and here's the reward that you got from that. So of course, here's a little example of this person with the dog. So the dog might be the agent. If you are trying to teach a dog to do a trick or to fetch a stick, you would throw the stick, right? And then the dog, the action would be to either return that stick or not return that stick. Every time the dog does not return the stick, they probably get nothing. If it's a mean owner, they'd probably get yelled at, which might be a slightly negative reward. Or if it's a good owner, then the dog brings the stick back, you give it a little treat. And then the dog says, oh, when I bring sticks, I get food. That's probably the thing I should do again in the future, right? So it's almost like training a pet. That's what reinforcement learning is. Now, there's two overarching ways to train like an animal or even a human if you wanted to. But one way would be to give it good things when it does something good. And the other way is to give it a negative reward when it does something bad, right? And in my opinion, far too many people give negative rewards to a dog who can't speak the language, right? It doesn't know what it's doing. So what's better, to give it a reward, to give it a positive reward when it does the good thing that you want it to do, or when it does one of the infinite things that is not what you want it to do, to yell at it or hit it or something, right? It's not gaining as much information from negative rewards as it is from the positive rewards. So if you look at it mathematically, it's way better to just be nice to somebody when they do the thing you want them to do, rather than be mean to them when they do the thing you don't want to do. So reinforcement learning, if we look at it a little bit more mathematically now, kind of looks like this loop. So we're introducing t now, and t, of course, is time. And any problem that we want to do inside a computer is going to involve some discrete time steps, right? So if we are doing reinforcement learning with an actual physical robot in the real world is kind of a continuous time problem. But in order to do this, of course, we're going to have to break this down into discrete observations, state, actions, and time steps. So the agent is in an environment. It's going to observe that environment and take some snapshot of it, analyze it, and say, okay, my policy says that at this state, I should do this action. So that's the action at time step t. That action is going to affect the environment somehow. The environment is then going to produce state t plus 1, so that's the state that the agent is going to observe at the next time step, as well as the reward for the next time step. The agent is going to look at, okay, here's the next state and here's the reward that I got from doing that action. Do I want to do that action more often or less often? That's essentially what's going to happen. So the agent or environment is going to interact in discrete time steps. So the agent observes a state at time step t. So that's st in some finite, possibly finite set of states. The agent is going to produce an action, at at the which is within the set of legal actions at that state at that time, because a legal action could depend on the time, right? Maybe it's out of gas or something. So the legal actions for a given state change over time. The environment gives us a resulting reward, rt plus 1, which is some real valued number. Then we transition to the next state st+1, which is again from that set of states of the environment. And if we want to look at this in a sort of linear fashion, the book likes to do this, so I'll copy what the book says, is that we are at some state t, we take an action, at, we get a reward, rt+1, which transitions us to state t+1, and then we take action t+1, reward t+2, so it's state, action, reward, state, action, reward, state, action, reward. That is the loop that we're going to be in for reinforcement learning. We can do this for all sorts of different problems, right? So our agent could be something playing a video game. Our actions could be the buttons that are currently being pressed on a controller. Those actions would affect the environment. So if I pressed the A button, Mario would jump. And so they'd be a little bit higher, maybe on the next frame of the game. And then we read the next frame of the game or the next state of the game. And we see the reward that we got from doing that thing. And then we update it, right? So we may see, for example, in a game like Mario, if our reward function, okay, what is the reward function? There could be many reward functions. Maybe we want to collect the most coins. Maybe we want to get the most points. Maybe we want to go to the right, Because most Mario games just running to the right to get to the end of the level. So, for example, if there were no enemies in the level that we had to jump over, if we pressed the right button, we would see that we will have moved to the right a little bit more. We will get a reward signal back, probably correlated to how far we have moved to the right. And then maybe on the next step, depending how I've updated my policy, maybe now I'll choose to go to the right more often. Similarly, if I chose to go to the left, maybe now my reward signal is negative. And so I'd update those values and choose not to go left in the future because going left last time was really bad, right? So this is sort of the really simple loop. So the overall workflow going from absolutely nothing all the way to a deployed reinforcement learning model sort of looks something like this. So in order to form the reinforcement learning problem, we have to think about our environment. We have to think about what our goal is in that environment and come up with a reward that suits that goal. Then we come up with whatever representation our agent is going to have for their policy. In our class, it's going to be just a big 2D array of values. So that would be tabular reinforcement learning. Here, this image that I borrowed from somewhere is using a neural net. So this would be just a little bit more complicated of a representation. Then we train the agent over time. That training could either happen in the real world on a real robot, or it could happen in a simulation. And then after we've done some sort of training, the output of this whole thing is a policy. And the policy just says, at this state, you should do that action, okay? And so then you would deploy that model somewhere to do whatever it is that you wanted to do. Let's have a look at an example. I'm going to show probably the two examples that are in the book, and probably two of the most well-known simple reinforcement learning problems. So this is called the cart-pole problem, and it's a balancing problem, right? So here you've got an agent, and this agent exists on a one-dimensional line, right? And so their actions are move a bit to the left and move a bit to the right. And essentially, you're just trying to balance this pole for as long as possible. As the thing tips to the left, you want to move to the left. Tips to the right, you want to move to the right, etc. So the actions then for this agent are move left and move right by some fixed amount. And if we want to, so what is our reward going to be? Well, that depends on what we want the agent to do. So in this problem, we want the agent to be able to balance the pole for as long as possible. This type of problem is going to be divided into what we call episodes. So this is an episodic task, meaning that it's going to start an episode. At some point, it will eventually finish that episode. And then based on the rewards from that episode, it's going to update its policy. But then it's going to be reset to some initial position, and it's all going to start again. So here, one episode might just have it start in the middle with the pole at some sort of like randomized angle. And if we want this to be balanced for as long as possible, then the reward could be, well, just a +1 for every time step that we keep the pole balanced. And so if we maximize this reward, we have maximized the balance time of the pole. So a lot of the times the thing we want to maximize is either related to minimizing distance or minimizing cost, in which case, if we want to, but in this case, it's maximizing time. So if it's maximizing time, typically we just give it some positive reward at each time step, and then we achieve our goal by just maximizing that. Like I said, this is an episodic task, so I think this particular version of the problem will reset if the pole falls to a certain amount where it's unrecoverable, or if the cart goes off the side. So maybe it's 10 units wide or something like that, and you're just fixing it within this particular area. So you see it resetting here, so it may have been falling, and so it just got reset. So that's one problem. But the issue here, the thing I want you to take away from this is not necessarily, oh, balancing things is interesting, but it's more so, okay, this is the environment, these are the actions, my goal was to do something for as long as possible, therefore the reward was positive for each time step, right? So taking a problem statement and transferring it into a reinforcement learning problem statement. That's the important thing I want you to take away with here. The next one is called the mountain car problem, and my face is probably going to be up here in the top right of the video. So for those people who can't see it, there's just a little goal flag up here at the top of this hill. So the mountain car problem, the goal is to escape to the top of the mountain as fast as possible. But the thing that makes this mountain car problem interesting is that the physics of this car, the engine of the car, is not powerful enough to just drive straight up the hill, right? So what it has to do is sort of, you've ever been like stuck in snow or something, this is the sort of thing you have to do, is like you go forward and you build up a little bit of momentum, then you go backwards, you build up momentum, and so it's like go to the right, go to the left, and each time you go back and forth, you're getting a little bit higher. It's almost like pushing yourself on a swing, right? To go higher and higher and higher, and then eventually you can escape this valley. And so the goal for the actions for the mountain car problem are just accelerate left or accelerate right. And the rewards, well, we want to get out of here as fast as possible. So it's the opposite of the last reward, where here, again, this is an episodic task. It's going to reset whenever we're able to reach the goal. And then here, it's -1 for each time step. So if we maximize a -1 for each time step, then this minimizes the total time to the goal. And in the assignment, we're going to see, okay, if we, I'm going to try and create a more fun assignment for you this year. It depends on whether or not I get it done in time. But last year's assignment was an assignment 1/2 like pathfinding problem, but we're using reinforcement learning instead. So if you are doing that pathfinding problem and you want to get the shortest path to the goal, then you just give -1 for each action. If you give -1 for each action, then maximizing that is minimizing the distance to the goal. And so that's the reinforcement learning way of minimizing distance, is to maximize negatives. And so here's what you see. You know, you start out, maybe you're taking these like weird sort of random actions that don't do much. You get into, as you do more and more of these training episodes, you get closer and closer. Maybe you start solving the problem a little bit, but then by the end, you've gotten to the optimal solution, hopefully, at some level of training. So, now that we know all these examples, what are the definitive elements of reinforcement learning problems? Well, first you have some agent in that environment, right, just like before. You have a policy, which is some sort of function that takes as its input the state, the time, and then produces an action that you want to do at that state, at that time. We have a reward function, which takes in a state and an action and produces a reward value. We have a value function, which is value is slightly different from reward, and we'll go into this in detail. But essentially, reward is what is my immediate reward from doing this right now. Value is what is the eventual sum of all the rewards that I will get if I follow this policy. And that is the thing that we really want to maximize, right? So for example, if I jump out of an airplane with no parachute and I'm falling through the air, what is my reward as I'm falling through the air? That might actually be kind of fun, right, to fall through the air unimpeded. It's the landing that's the problem, right? So my reward function from being 3,000 feet above the ground, my reward for that is probably pretty neutral, right? But my value of being hurtling toward the ground is very negative, right? Because the eventual thing that will happen will be extremely negative, right? It's not the fall that kills you, it's the landing. So those are the differences between reward and value. We'll talk about the mathematics of those. And optionally, we can use a model of our environment. What do I mean by a model of the environment? Here, a model of the environment means a simulation of an environment. So in order to do any of our search algorithms that we've looked at so far, we need to have a model of the environment, because search relies on looking forward through this path of actions that I can take. So for example, if we're playing chess, right, I actually need to produce the next, I need to know the legal actions at a particular state. I need to be able to implement those actions, see what the next state is. So all of my simulation, my search program, needs to have a chess simulator that can look 20 moves in the future and see what is actually happening. That is not the case for reinforcement learning. You could have a robot walking around the room. And as the robot, maybe you want to make a Roomba, right? So as you suck something off the ground and you can detect that, positive reward. If you bump into the wall, negative reward. But you don't need to know the physics of the universe or how vacuums work or any of that, right? You don't need to know how applying voltage to my left wheel affects the turning radius or anything like that. It's just, I was in this state, I took this action, and I got this reward. Now, if you don't have a model, then your training is going to have to take place in real time, in the real world, right? So having a model is always beneficial, because if it's very accurate, then imagine how much faster we could simulate the Roomba training than actually putting the Roomba in the room. We could do millions or billions of operations per second rather than just waiting for it to hopefully suck up some dirt, right? So models of the environment are optional. That's one of the downsides of search, is that we need a model. We have to have it, right? Because we're doing the simulation ourselves. But reinforcement learning does away with that. Now, the downside of reinforcement learning is that because it is a learning algorithm, it's going to need a ton of training samples in order to learn the true values, right? So the downside of machine learning is the amount of data or samples or episodes that you actually need. So search doesn't need episodes, it doesn't need data, doesn't need any training data, but it does need a model. So search is not always great, learning is not always great, there's a trade-off between the two. The policy in reinforcement learning, as we know now, it's a mapping from states of the environments to actions to be taken at those states. This could be a simple lookup table, which it will be in our assignment, or a complex computation such as a neural network, for example. It is the core of the reinforcement learning agent. It defines the behavior, and it is the eventual thing that we care about. All we really care about is producing that policy that does the thing well. Plays chess well, guides the Roomba, whatever, right? And the cool thing is that reinforcement learning policy may be deterministic, it may be stochastic. So you could have a policy that says, right here, you want to go left all the time. But it could also say, if it was poker, 30% of the time you want to bet, 50% of the time you want to call, and 20% of the time you want to fold, right? Because there are optimal policies that exist in some environments which are stochastic. You don't always want to do the same thing all the time in poker, because then someone will know, oh, Dave just bet. That means he's got a really good hand, right? You don't want to always fall into that trap. So policies in reinforcement learning can be deterministic or not. So the policy at some time step t is called pi sub t, because our policy is going to change as we learn. So our policy that we started out with is not necessarily going to be the policy that we end with. So policy is going to map from states to the probability of taking an action at that state. So what we actually get in the general case is a probability distribution inside the policy rather than just take this action. So pi sub t at SA is probability. This is the probability that the agent should take action A sub t when we have state S sub t. Okay, so I'm at a given state at a particular time, and I'm looking at this action. Should I do that action? Well, here is the probability of which you should do that action. That's what the policy says. So reinforcement learning methods and RL algorithms specify how the agent changes its policy over time as it learns. So how do I go from thinking I should touch the hot stove into not touching the hot stove? That's the algorithm, right? So what we're going to see is that we're going to hold some value associated with doing actions at states. Probably, let's assign them, for example, all 0 to start with. So the first time I encounter a situation, I'm like a baby, right? I don't know what is that hot stove, right? So I'm going to try to touch it once, right? The first time I see it, maybe I don't touch it. The second time, maybe I do touch it. And now I've got this hugely negative reward. So now my value, instead of being 0, maybe it's negative 1,000 or something like that, right? And it's going to take me a lot of cold stove touching in the future to think, okay, maybe it's safe to touch a hot stove again, right? So that's how you do it. You just store some value associated with the return over time that you get from doing that action at that state. When you get new rewards, you update your belief. It's just, what is the math involved in updating that belief? Well, that's reinforcement learning. So the agent's goal is to form a policy that gets as much reward as it can over time. So here is the current state of our final assignment. This is the solved policy that you're trying to get. So unlike assignment 1 and assignment 2, here you've actually got an agent that is occupying a single place in this environment. What the agent is going to do is try one of these actions based on its policy. So for here, what this policy represents right now is that if you see a line pointing in a particular direction, or multiple directions, it says you should equiprobably choose one of the actions that I am pointing to. Why? Because those actions will lead you to a goal the fastest. And so these green areas are the goals. So for example, where the agent is right now, it says move left. And so we move left, we would go here, move left, go here, move left. Now we're at the goal. Down here you can say it says I don't care where you go in any direction. Why? Because it turns out that if we do go in any direction, we can still get to that's still on the shortest path. So for example, if we go left or down, we'll still get to this one as quickly. If we go up or right, we'll still get to this one as quickly. Now that's a rare case, but you can see how that works. Similarly, here is a blackjack policy. I am going to be using blackjack as an example for reinforcement learning because I think it's a really intuitive, fun type of example. And so I'll be showing the rules to blackjack later. If you have never played blackjack, don't play it for money because you'll lose, right? That's the whole point of blackjack, is the casino takes your money. But just play it with some friends or something like that. It's an interesting game to think about. So what this policy states essentially is that if the player, you, have these cards and the dealer is showing this card, here's what you should do, right? And it turns out if you can memorize this table perfectly and go to a casino, you're losing over time about 2% of your money, right? Now, obviously, you're not betting infinitely small amounts. So you might go up $50, then down 100, then up 200 or whatever. But if you play infinite hands of blackjack, your return on investment is about 48%. That's how it works. Okay. Oh, sorry. I guess 98% if you want to look at it that way. So if 0.5 means you are even, then it's 0.48 is what you'll get from playing optimal blackjack. Now, you might say, what about card counting? Maybe I'll talk about that later. There's a way that you can sort of beat the casino if you remember what cards they have left in the deck, because the probabilities change and stuff, but they'll just kick you out if you end up doing that. So don't worry about that. The reward function. This defines the goal in a reinforcement learning problem, and it maps each perceived state or state action pair, so that a state action pair just means doing an action at a particular state, to a single number. So touching hot stove equals -1,000, something like that. The reward comes from the environment, not the agent. The return is the sum of agent rewards over time. And so the RL agent's goal is to maximize return. So technically, it is not maximizing reward, it is maximizing return, right? Because again, the falling airplane, from the airplane example, no matter what I do, I'm going to get the same reward. It's the eventual landing that's the problem, right? So I guess the whole point of that is not to jump out of the airplane in the first place. Ideally, that's what the reinforcement learning tells you. So in biology, the reward might be pleasure or pain, like the satisfying of hunger from eating something, or the pain of running with scissors and getting stabbed or something like that. So here's some examples. We've already kind of gone over these. So if you have pathfinding, then the goal would be sort of a terminal state that restarts that episode. So non-goal states would have a -1 reward, and then that means that maximizing your reward is minimizing the negative number, which means that you're pathfinding in the shortest amount of time. In blackjack, maybe a winning state would be a positive reward, a losing state would be a negative reward, and the reward would be proportional to the amount of money that you won or lost, right? So if we're just playing blackjack and we're betting $1 every hand, then if I win, I get another $1, so my reward is +1. If I draw or push a hand of blackjack, then I get my money back, so the reward will be 0. If I lose, then the dealer takes my money, so the reward will be -1, right? So we can learn how to play blackjack by doing that. If we're playing video games, for example, here's a cool animation that I found online of someone using reinforcement learning to play Super Mario World, or some emulated copy of Super Mario World. And the reward here was to go to the right? So they're learning over time. They've taken this image, which is like a large actual version. They have miniaturized and discretized this space into a very, very small input image that still somehow represents the game. But because the complexity of your state and action space is going to affect how long it takes to train, typically what you want to do is take a problem and reduce it to the minimum possible representation of that is still usable, right? So as a player, yeah, it might be nice to have all these fancy graphics, but you certainly don't need to take all of those graphics into account to actually play the game properly, right? As a player, you pretty quickly realize that like all these background leaves and stuff, they actually don't affect gameplay. Those are just like graphics that make the game look better. So yeah, so we could, if we wanted to, we could take those away or whatever, depending on what we want to do. Returns. We talked a little bit about returns. The agent gets a reward at each time step. So RT, T+1, T+2, up until some terminal state. What value do we want to maximize? Technically, we want to maximize the expected return. So this big E, that is the expected value. And the expected value is essentially just, if we did this 1 trillion times, what would the average be? Right? So that's the expectation. We might get lucky or unlucky, but we're trying to average these over time. And for whatever reason, the symbol for return is big G. Okay, so big G of T. So for episodic tasks, meaning that the tasks do end and restart somehow, the return is G of T, where it's RT plus RT plus 1 plus RT plus 2 all the way to some terminal time step, capital T. So the return of G of lowercase t is the sum of all the rewards from time step t, which may or may not be the beginning, but from time step t all the way to the end step. And then an optimal policy, pi star, is the one that maximizes expected return. So we're going to come up with a policy eventually, and if that is the optimal policy, then we will get from that, if we play it enough times, the best possible policy, which maximizes expected return. But if there is randomness, it doesn't mean that the optimal policy, we are always going to win. right? In fact, for something like blackjack, it still means we're going to lose over time. So optimal policy doesn't mean it's benefiting us or it's making us money or whatever. It just means it's the best that we can do given this problem statement. The value function. So if rewards are, yep. We'll get, yeah, so the question was, what if it's not an episodic task? Like a Roomba is not an episodic task. It just goes around all the time. We will introduce in a lecture or two the framework for something called continuing tasks, which are not episodic, but there's a nice little mathematical trick that we can do to treat them all as infinite episodes, essentially. We'll get to that though, yeah.
I was thinking about like the hill climber.
Yep.
What if you just like never gets out and you just stay there for forever?
Well, you eventually do get out because, and we'll talk about this again, if you keep trying things and keep getting negative rewards, then you will eventually not do those things. And you will do the thing that will get you out, eventually. There are tricks and tips about how to most effectively update the math and stuff, but one of the things, I guess this most directly applies to your question, is just like we had bounds on the cart pole problem, is that what I called it? The pole balancing problem. We could say if the pole has been balanced for 1,000 time steps, reset it, right? Because we're not necessarily concerned with, okay, it's perfectly balanced. I'm learning about it being perfectly balanced. I want to learn about the other stuff too. So we could prematurely cut off episodes, just like the mountain car problem. We could say, okay, if we haven't gotten far enough in a certain amount of time, then artificially cut off the episode and restart it. I think that's what most people do. But there's also another class of problems called continuing tasks, which you wouldn't want to do that. Yeah. All right, so the value function. If rewards are what are immediately good, then value functions indicate what may eventually be good or bad on expectation. So the value of a state or state action pair is the total amount of reward an agent can expect to accumulate in the future given that is currently, in this state. So again, just to drive it home, the example of falling through the sky, the immediate reward is probably not that bad, but the value should be horrendous because of the eventual thing that will happen. Value indicates long-term desirability. If we're thinking about, actual pathfinding in the real world, you ever been in a situation where you've got to, you're walking to the bathroom or something. Do you step on the Legos or do you go around the kitchen island? Right? Like which one, maybe it's fine to step on a Lego to have a little bit of a negative reward just to get there faster, right? There's all sorts of things that we can consider. So if reward is pleasure or pain, then value is sort of how pleased or displeased we are to be there. They are definitely correlated, but they're not the same thing. So we seek actions that have the highest value. Those will bring the highest eventual return, not necessarily the actions that have the highest reward. Value is harder to determine than reward, so we must calculate and estimate them. So another example from everyday life, hopefully I'm not the only one who can sympathize with this, but you're up late, it's 2 a.m., you're working, and there's a bag of cookies right there. Huge immediate reward from having a few cookies. But the expected return of eating cookies every time you're working, maybe not so good, right? So as humans, sometimes it's hard to get out of the trap of falling for immediate reward, but it's the eventual return that we want to learn about. So our policy, ideally, should take high-valued actions for each possible state. Value function examples. So these are the same things as last time, but for value rather than reward. So for pathfinding, non-goal states on the best path to the goal has high desirability and a high value. So actions taking us on the path have high value, right? So for example, if we're doing pathfinding and we said, okay, every action, it just gives a -1 reward. Well, just relying on reward, we have no idea where to go. because every single action will give us the exact same reward. But it's that value that keeps track of over time, okay, if I get -1 from every time step, let's say, for example, we've trained our model. Well, a state that is 5 distance away from the goal should have a value approximately of -5 to indicate that, okay, I want to go from this state to another state that has a lower value because I'm getting closer to the goal. Lower meaning more positive, not more negative. Sorry about the confusion. But the value should tell us something. The value of a state is how maybe close to our goal we are or how desirable it is to be here, even though the rewards we get from taking all the actions are the same. In blackjack, let's say I have a 20, which is really good hand. It's almost the best possible hand. The dealer has a 6, which is the worst possible hand for the dealer because they have a very high chance of busting, of going over 21. So this state has a very high value for me. Now, it doesn't mean that I'm always going to get the best reward because I can still lose. And if my performance at casinos has anything to say about this, I'm probably going to lose, right? Like the dealer just always gets the perfect cards at the perfect time, right? So if the dealer gets flipped over a 10, 16, 5, 21, player loses, like every time, right? Not really every time, but this is one of the higher valued states, meaning we want to be in that state. It is very good. Even though we can't predict the exact reward that we're going to get in this episode, what our value will show us over time that it is profitable to be at this state. We want to be here if possible. Or more explicitly, what we will find out is more important than state values are state action pair values. So being at 20 with the dealer showing a 6, the value of me hitting at that state is very low because I have a very high chance of busting. The value of me sticking at that state is very high because I have a high chance of winning. Okay, so it's not just state values that we're interested in, but the values of doing actions at those states. All right, I talked about the model of the environment a little bit. This is essentially a simulation. That's what type of model. I'm not talking about a reinforcement learning model or a machine learned model here, but just some way of simulating the environment. The cool thing about reinforcement learning is that if I had a big blackjack table written on a whiteboard or a chalkboard or something, the two of you could sit down and play blackjack, and I could write on the board, you won this, update your value, scratch it out, put in a new one. Oh, you lost this hand, scratch that out, put in a value. And that is doing reinforcement learning. I don't need to know the rules of blackjack. I just need to know the states, the actions, and the rewards, right? Having a model that simulates blackjack is obviously, we can play trillions of hands, right, over the course of a few minutes. So we would want that, but we don't need one. That's cool. So a model, given the state and action, the model may attempt to predict the next state. Actually, a really cool modern area of research is in neural networks that predict the outcomes of things. So for example, if we're trying to play Super Mario Brothers, but we don't have a model, it might be really slow because we just have to play the game in real time. But what some neural networks do is take as input the state of the game and the action that you want to do, and then as output, predict the next state of the game. So you've almost got a neural network that plays Mario, but simulates it, not actually plays it, right? So in that way, it may be possible for you to play a simulation of something that is not exact. And if you get a decent policy in that simulated environment that may not be exact, the policy that you learn may still be applicable to the real world or the real problem. So when we do stuff like planning or search, we do need models. It's just built straight into the problem. We need to be able to look ahead and rewind and all sorts of stuff. Not necessarily the case for reinforcement learning in general, but it is often used in games, right? Another really cool thing about learning is that we don't even need to play the game. I could go on some chess database, download all the chess notation replays of games, and do learning based on what other people have done in the past, right? And we'll see in the future that when Google DeepMind created AlphaGo, the system that beat the world champion at Go, one of the first versions of that program, that's what it did. It took a database of possibly millions of expert human games. I don't know exactly how many they had. And then instead of starting the reinforcement learning training from scratch with a random policy, it started by mimicking human play in that way. So that's a way that you can use reinforcement learning without needing any model or anyone actually playing the game. It's pretty cool. What we'll see is one of the main concepts in reinforcement learning and in life in general, I'll have like a whole thing, I'll have a whole lecture about this, is exploration versus exploitation. It's one of the main challenges is to balance exploring versus exploiting. What does that mean? Well, to obtain a lot of reward, you have to prefer actions that you know produce good results, right? So for example, I know that moving left here gives me some health potion or something, right? So I'll keep doing that. But in order to learn which actions produce good results in the first place, we have to explore and take other actions. We can't always just do the first thing that comes to our mind. So the agent must exploit knowledge that it has, but it has to explore in order to gain more knowledge. And this is one of the main challenges in like real life. So here's a real life okay, put your hand up if you can give me a real world example of exploitation versus exploration in real life. You have all done this, and you all do it every single day. And hopefully someone can guess the thing that I have. So, exploitation is doing something that you know is probably pretty good, right? Exploration is having to try something new in order to figure out the things that are good. What have you heard this called before? Risk versus reward. Okay, what was that example? Okay, and so the answer was eating. In what way? There you go. There you go. Okay, this is always. It's the canonical example, right? Go to the place that you know is all right. It's pretty cheap. Or do you want to try a place that you've never been before? Sometimes that works out, sometimes it doesn't. Here's my example. Since junior high, basically, I have gone like explicitly to Wendy's, right? Love Wendy's, great. Well, maybe not so much if you're trying to buy Canadian. Wendy's is not a Canadian company. But always loved the classic double combo from Wendy's, or the junior bacon cheeseburger, whatever. Lots of good stuff at Wendy's. I'm not affiliated. I'm not going to have an ad for Wendy's here.
You don't even need a Dave's burger?
I don't. So here's the thing though. Last year sometime, a friend of mine insisted that we go to Dairy Queen. And I'm like, but I'm in the mood for a burger. I don't know, like it's an ice cream shop. And I'll be damned if the Dairy Queen burger is not better than a Wendy's burger. I don't know if it's just the Dairy Queen on Portugal Cove Road or whatever, but you know how they have the picture of the burger and then it's what you actually like, what you get, what you expected versus what you really get. It looks like the picture. It's like actually made well and it's good quality. So that was an example of that. I mean, maybe you shouldn't be eating as much fast food as I do, but I probably get more Dairy Queen than I used to now. Now maybe, I don't know, the new McDonald's Big Mac 2.0 or whatever will come out and I'll have to try that. But it's a real thing, right? I'm sure you've all done this with like, a friend or a partner. What place are we going to go? Oh, let's just go to the place we know. Or, oh, the new place opened up. And you go there and it kind of sucks. Or it's expensive, but you've already ordered. And like, it's just exploitation versus exploration. It's a real life problem, right? It's also a problem in like relationships, right? You're dating this person. They're fine. Is there someone better? Now, unfortunately in that problem, it's much harder to explore because you can't just go back and get Wendy's after you've tried Dairy Queen, right? It might not work out so well. But But just think about, I like this example because it's like, everyone knows that one couple that's been together since like high school or whatever, right? But if I told you that in high school, I tried McDonald's once and then I never ate anywhere else for the rest of my life, you'd probably call me crazy. But somehow that's romantic if it's a relationship, right? It is weird, but anyway. Okay, don't quote me on that. That won't be on the exam. All right, again, playing, other sorts of games. Okay, choose door number whatever, right? One has a dragon, one has 1,000,000 gold pieces. I chose door number 3 last time. Do I try it again? Well, it had 10 gold pieces. 10 gold pieces is pretty cool. But maybe the other one has 100 gold pieces. Or maybe the same door doesn't even have the same thing, right? I go back to Wendy's and the guy who made my burger is like upset at the manager for whatever reason and like makes my burger poorly. Well, come on, man, I was expecting this. So now, again, it's not the reward, it's the expected return over time, right? You got to go to the place that gives you consistently the best stuff, not the place that one time gave you a bunch of things, right? Or that were good. So that's reinforcement learning. That's what we're going to be learning. I know this was kind of heavy on the storytelling and light on the math, but trust me, that's what the next 3 lectures are going to be about.